Hello, everyone. Welcome to our live session on biogas sanitation, what is realized as part of the Octopus platform, Octopus standing for Operational Collaborative Tool of Ongoing Practices in Urgent Sanitation. And this is a first collaborative online platform about emergency fecal sludge treatment and disposal, created by Solidarité International. And Octopus aims to provide a space for knowledge sharing and guide people, practitioners, and policymakers when it comes to fecal sludge in emergency settings. And my name is Stefanie Abulasin-Thieme, and I'm from UPM Umwelt-Projekt-Management GmbH that assisted or supported Solidarité International in this venture for implementing also certain trainings. On the Octopus platform, whose link you find on this slide, and that will also be shared later with you, you find several trainings on different topics. So the topics are particular biogas sanitation, effluent management, and sludge and biosolid management. And these trainings basically provide you knowledge on fecal sludge management in emergency settings, and also are intended to enable you to make more well-informed decisions on these different topics. The trainings are self-paced, so if you do them, you can take a break whenever you want. You can jump into topic here and there as you like and as your preference or as your knowledge gap. And if you complete the entire training, you will also receive a certificate. And to make it a bit interactive and fun, the trainings are complemented by some videos and also some quizzes. So today on this live session, this is complementary to the training on biogas sanitation. And online, on the training for biogas sanitation has the learning objective to introduce the basics of anaerobic digestion and biogas recovery and provide insights on practical solutions when it comes to biogas sanitation, and thereby covering different topics from the basics to digestion technologies, process parameters, biogas installation planning, operation and maintenance, and also specifically dives into a specific example on a sanitation biogas plant in the Rohingya refugee camp in Bangladesh, Cox's Bazar in Bangladesh. Now, this is quite extended, and so this live session to the training will just focus on some parts of the online training. So it's complementary, and I very much encourage you to also check out the platform and the trainings itself. So in this next hour, within the next hour, I want to just explain to you why biogas technology, what is the biogas potential from fecal sludge, which parameters influence the biogas production, what are possible biogas systems, and also here want to already broadly present to you the experience of biogas in the refugee camp with some common challenges and solutions that are possible. Before we start, I just want to mention that this session is being recorded. The recording as well as the slides are shared with you afterwards. Then we have the chat, where I very much encourage you to leave comments, questions, reactions, and exchange with the other participants. Then I would like to ask you, as you're all already doing perfectly, to keep your microphone and camera closed while the others are presenting and speaking, what is mostly me, unless you give me a hand sign and would like to ask or talk yourself. And then you're also very much encouraged to raise your hand, react, and interact as much as possible. This session is not a regular webinar, but we try to, keep it a bit interactive. And without further ado, we already have here the first interaction, where I would like to just tell me, what do you associate with biogas sanitation? For this, I would like to ask you to scan the QR code or go on to menti.com and use the code that you see up here, 41879401, and would like you to answer with some keywords. Just what do you associate with biogas sanitation? Whatever comes to your mind when you hear biogas sanitation. Very nice. Some very good points already. Great. So yeah, there's coming a lot in regards to energy, renewable energy, energy for free, electricity, sustainable fuel for cooking. That's a lot of good points that mostly focus on the energy aspect of biogas. Ah, shit happens. Good. This is related to the sanitation part. Exactly. Because biogas sanitation, as the word combination already says, brings biogas and sanitation aspects together. And that brings me right away to why biogas technology. What are the benefits? So you named already very well that it is a renewable energy source, that we can produce biogas from any arising organic waste. Now, when we look into a camp setting, we have mostly organic waste, maybe from food waste or kitchen waste, but a lot from excreta, wastewater, and sludge from toilets. And there are also possibly toilet paper and other tissues that are disposed. Further waste may arise from agricultural waste, manures from animals like cows or pigs or whatever you have in your region. And all this organic waste goes into this so-called biogas digester, where anaerobic digestion happens. Anaerobic implying that there's no oxygen or air entering the system. And throughout this time period, even monodigestion or co-digestion, which just implies if you have one feedstock or several different feedstock, meaning you, for example, combine your fecal sludge or the toilet waste you have with the food waste that arises or the manure from your animals that you have at home. If you combine them and leave them in this closed system, over time you will produce biogas. And usually the systems, depending on the efficiency and setup, it is possible to convert 40 to 90% of the organic matter into biogas. And at the same time, you also have the digested, what is the, let's say, liquid left over, or nutrient-rich slurry often also, that has very interesting nutrient characteristics and could be further used, depending also what is your initial feedstock. It may need further post-treatment before it can be applied for different purposes, such as in agriculture. So this is especially the waste to value aspect, but at the same time, when you look at waste to value, then it also implies that biogas technology provides a waste management solution for your excreta. Instead of open defecation or simple septic tanks, we replace it with a biogas digester. and emissions that would arise anyways, emissions so-called also biogas, will be captured and made use of. Now, this biogas has a very diverse application possibilities. Here, starting with the cooking, by just taking the regular biogas, maybe cleaning it a bit, just to connect it directly to your biogas stoves or modify the gas burners. Then you can use biogas to produce electricity by using small generators, biogas generators, or combined electricity and heat generators. Then, if possible, and on a higher scale, you could possibly upgrade it to biomethane and use this biomethane as a fuel. Then you could use biogas for lighting. There are specific gas lamps that can be supplied with biogas directly. Or is it possible to use the heat energy and thereby use this for turn it into refrigeration? And last but not least, it is possible to use also biogas for steam generation or hot water production that then can be used for different purposes, including for the optimization of the biogas process itself. Because often when you use fecal sludge as a feedstock, you may also have pathogens inside your digested, and to avoid this, it's possible to use the heat for pasteurization to eliminate these pathogens. So you see, in summary, biogas brings a renewable energy solution with very diverse applications, and at the same time provides a sustainable waste or sanitation solution. And that brings me to our next interactive thing, where I would like you to scan the QR code again. And here we have a little game where at the end we also see how everybody is participating in this session in a fun way. We're 6 players already. And I've prepared certain quiz questions for you. And the faster and correcter you answer, the better the results will be at the end. So the first question is, what is the limitation regarding anaerobic digestion? And we have 4 more seconds for answers. Voilà. So in fact, the technical complexity is often a limitation. Nutrient-rich digested conversion, this is not a limitation, but something that we aspire. As I mentioned, the biogas technology has the benefit to produce the biogas that can be used, and the other output is the digested, that is usually rich in nutrients and can be used directly on the fields or need further post-treatment, such as composting, to be used. But the technical complexity is referring that you usually need skilled craftsmen, experienced and skilled craftsmen for the design and construction of your biogas digesters. And there is also a certain complexity to the operation and maintenance in comparison to other options, such as a simple septic tank. And this may always pose a challenge in managing and optimizing the anaerobic digestion process. But what now is actually the biogas potential of fecal sludge? And this is very variable. So here we have the biogas potential from different results. First, we have kitchen waste and human feces combined, then bio waste, fecal sludge from septic tanks, and excreta undigested, meaning be fresh. So looking at the lower 2 points, first of all, fecal sludge from septic tanks. Usually the potential is quite low, but in general can be very much depending on how long your fecal sludge is stored in the septic tank. Some people, depending also on the volume of your septic tank, may desludge the septic tank every 6 months. Others do it every 2 years. So by the time the fecal sludge arrives at the treatment system or a centralized biogas treatment plant, the fecal sludge may have been already mostly digested in the septic tank and may have produced their biogas that was just uncontrolled, released into the environment. So that compares to the excreta undigested and fresh, that has a much higher biogas potential compared to this. Because here in that case, you would replace the septic tanks. So the excreta, the toilet waste is directly flushed into a biogas system and used. And there, in this upper example, you can see if you combine human feces with other co-feedstocks such as kitchen waste, you can increase your biogas production substantially. Other than the retention time in the septic tank and these conditions that I just described, there are a variety of other parameters that influence the biogas production. Just to name the major ones, these are temperature, the pH level, the retention time within your digester, the carbon-nitrogen ratio of your input feedstock, the organic loading rate, the total and volatile solids of your feedstock, as well as the chemical and biochemical oxygen demand. Now here, let's, for example, dive into the temperature aspect. Now, when it comes to temperatures, it is usually said with low temperatures, you have low microbial activity. So it is recommended to operate your digester at least at 15 degrees Celsius. Below, it may require some heating. The higher you go now with your temperature, the higher the microbial activity, the higher the biogas production rate, and also the lower the retention time or the time needed to have the high biogas production. So along this diagram, you see that there is a division into 3 temperature intervals. You have the psychophile, the mesophile, and the thermophile temperature range. And as I mentioned now, the higher the temperature, the better the micro activity that would refer to the thermophile. So this is really in favor for high methane production and all. But at the same time, the thermophile or thermophilic temperature range is also faced with some challenges because it is also considered a bit more unstable. That means if your temperature drops suddenly, already just for 5 degrees Celsius, or increases very rapidly, it can interfere with the microbial activity and even in a worst case, stop your biogas production at all. So in practice, unless you can really guarantee that these high temperatures can be sustained continuously without interference, it is recommended to sustain a more mesophilic temperature range between 30 to 40 degrees Celsius. This is especially more easily to be realized in the warmer areas or the southern parts of this southern continents like Africa or Southeast Asia. And so the optimal temperature range is usually between 35 and 40 degrees Celsius. And at this range, you also guarantee a more stable process where sudden temperature changes are not desirable, but will not destroy your microbial activity. So here again, I would like you to pay short attention and answer the next question as part of our quiz. Okay, let's do this. Which temperature range provides more process stability in anaerobic digestion due to the greater diversity of microorganisms? And I hope you all paid attention and I explained it well. Then the answer should be relatively easy for all of you. Yes. So I think my explanation was well received, showing that the result, all of you picked mesophilic. Very good. So now for the next one, which parameters influencing biogas production would you like to learn more about? Okay, Zubin, you lift your hand.
Heather, could you please explain the retention time, please?
Okay, thank you. Okay, then let's dive into the retention time. When we look at the retention time, we differentiate between the hydraulic retention time and the solids retention time. The hydraulic retention time refers to the duration that the raw material remains in the digester, and the solids retention time refers to the specifically to the solid particles or sludge remaining in the digester. So, depending on your digester design, both times can be the same, but in some cases, again, depending on the design, also the sludge remains longer in your digester, so the solids retention time may be longer than the hydraulic retention time. And overall, the retention time is calculated by dividing the digester volume by the flow rate of the substrate influent. And when we look in the relation between temperature and retention time, then we have to consider that colder environments also require a longer retention time. So this is what I also referred to before when we were talking about temperature, that the microbial activity is lower with lower temperatures. So to have a similar biogas production at the end achieved, you would need a longer retention time within the digester. So this compares, for example, if you have a digester in an environment of 10 to 15 degrees Celsius, then it may need 55 days. But then if you go to temperatures above 20 degrees Celsius, then your retention time lowers itself to only 30 days. So all this at the end, you have to consider when you design your digester. You look at the environment, what is your surrounding, you look at and you look mainly also at the amount of substrate you have. And combining this, you will calculate the volume of your digester. Now, every substrate may also have a different timing, and otherwise how long it takes for a substrate to produce the majority of its biogas potential to reach its majority of biogas potential. And that you usually do based on tests in laboratories. So here again, I want you to join me in the quiz and answer this Mentimeter question. We have 2 players missing. One. Very nice. Thank you all for your participation in this. For what would be the retention time for a digestible volume of 10 cubic meters and substrate inflow rate of 0.5 cubic meters per day? So this is a small calculation. And if you remember, you basically have to divide the volume by the substrate inflow rate. Very well. So I think you understood the principle very well, showing that the result of all of you is very correct, very good. So looking at the time, we could have one more parameter that we can cover, and the remaining parameters you can explore later in the online training, also when I share with you the presentation. But which third parameter would you like to look into or learn more about? Any preference? Okay, Martin, please.
Well, I would be interested in the carbon-nitrogen ratio.
Okay, thank you. So let's look at the carbon-nitrogen ratio. So that the carbon-nitrogen ratio you can always see as some kind of balance between the carbon availability and the nitrogen content in your feedstock. While the microbes basically need both carbon for the energy and nitrogen for the growth to produce biogas. And if you have too much, like for example, if there's too much carbon, meaning a very high carbon-nitrogen ratio, the microbes run out of nitrogen, what consequently slows down your biogas production. And what happens if there's too much nitrogen on the other hand, meaning a low carbon-nitrogen ratio? Then it can turn into ammonia. And too much ammonia can harm the microbes and stop biogas production. So the ideal ratio that you have is shown here, lies between 16 to 25 to 1. Now this balance may not always be reached by one feedstock, like for example, the fecal sludge may be very high in nitrogen. So what to do is that in that moment you aim more for co-digestion, bringing in some other feedstock that is higher in carbon, then again, to reach this balance and this ratio. So you need to always at the beginning test your feedstock and then combine and see how the results are. And the information on carbon nitrogen are usually in a first glance. When you do just like a first feasibility, you can already find a lot of information on that online. So I hope that explains it well. And here again, we have like a little test questions to just see. Is the 6th player coming or we just proceed with 5? Okay, let's proceed with 5 people. And the question is, what is the optimal carbon-nitrogen ratio range for anaerobic digestion to balance carbon availability and nitrogen content? Very good. You all pay very good attention. Very happy about this. So looking at the time, I would say, really, I would encourage you to check out the online training, and would like to proceed with you for now to what are possible biogas systems, to just visualize them a bit for you. What are the most common digester types that you can find worldwide? And one of the most common one is the fixed dome digester. What is an underground digester with a fixed non-movable gas holder on the top, as you can see here, usually using bricks, concrete, and cement to plaster to build. And in this schema next to the picture, you see, can you see my arrow when I show something on the screen right now? Let's see. Can you see this? Yes, that you should see. So I just highlighted the inlet that brings the substrate to the bottom of your digester. And the biogas always rises into the air. So here you have the biogas outlet, and your digested at the end will leave through here. And the advantages of such a fixed dome digester is that the relatively low initial investment costs. Also because it's such an established system, there are craftsmen that are usually experienced with this kind of constructions. There are no parts that move or lose. Usually doesn't require necessarily pumps or mixers, and is, if well constructed, has a very long service life. Nonetheless, it may be difficult to maintain since it's an underground installation, and it requires precise planning and experienced masons. But again, since it's one of the most common digester, there are usually also experienced masons to be found. Alternatively, we have here a floating dome digester. This again is also an underground constructed digester, but the difference is you have an open top and an above ground gas holder, a so-called drum that is inserted into the digester, what you can see here at the end. And this gas holder goes up and down depending on how much gas is inside. So if it is full, the gas holder will be up, very much up. And if you use the gas, then it will go down. But other than this, the principle of the generation is very similar. And here also the pro or a positive aspects is that it's relatively easy in the construction. And you have a visible biogas production. So as an operator, you always see how much gas you may have. And you have a very constant gas pressure. Compared to the fixed dome digester, nonetheless, there may be a bit of an increased space requirement, and you may have higher initial investment costs, since the drum that goes up and down is usually a steel drum. And you would also need regular maintenance of the steel drum. And if you don't use the biogas, but your steel drum is completely filled already, it may be possible that the biogas leaks into the air by just coming through the sides here around. Now another type, we have the balloon type digester. This is basically a weather-resistant plastic or rubber bag with a usually long shape. And it serves again as a combination of digester as well as biogas holder, storing the gas in the balloon's upper portion, as you can see here in the picture. And the longer shape ensures that once the input goes in, it stays relatively long within the digester, because it is then always just pushed slightly towards the outlet with every new substrate this is being injected. Again, here also you see a bit how much biogas is being produced by how strong the rubber bag is. And to increase pressure, you may put something on top of your rubber bag, as you can see here. It seems to make it a bit heavier, so the biogas is more pushed towards the place of use. And the advantage of such system is that it's prefabricated and related to low costs, easy to transport and install, and also more uncomplicated to empty and maintain. What is especially suitable for areas with high groundwater tables, because here you don't have anything underground, and it's usually also, due to its prefabrication, a low risk of any leakage. Nonetheless, it may have a lower lifespan. There's a potential risk for mechanical damage, and you may have also an increased space requirement since it is not underground but above ground. Here, a little test again to see how it goes with your attention throughout this presentation. Yeah. Nice. So we have 5 players again. Really good. Let's see. Which of the following factors influences the selection of construction material and the overall design of a biogas digester? And I think here I explained some of the factors. I mean, they're the most essential. And let's see. Yeah, I think it was a clear answer for all. Very nice. Now I want to look more specifically when it comes to sanitation installations. The biogas digesters I just presented, they are not only for biogas, for sanitation aspects, but can also be used for agriculture waste or any other organic waste. So here, when it comes to biogas sanitation installations, most commonly we can find the biogas settler and biogas septic tank, the anaerobic buffered reactor with biogas production, and the anaerobic lagoon. So the biogas settler or biogas septic tank may be connected, as shown here in the schemata, directly with your toilet. And from your toilet, it goes directly into the biogas tank. Now, the advantage of such a system is usually when it's not connected to a sewer. The obvious advantage is that it requires less water in your toilet system. And also, if you have a direct connection to the biogas tank and don't store the sludge first until it's collected and transported to a more centralized system, then, as I mentioned, you have also a potential for higher biogas production. Other than this, the functioning is relatively similar to the dome digester that we presented or discussed before. Here, alternatively, we have shown the anaerobic buffered reactor with biogas production. This is several steps what increases the treatment outcome, especially when it comes to the digested. So in this example, you have the fecal sludge or toilet waste going firstly into your biogas settler that I presented before, and then it goes into an anaerobic buffered reactor. Anaerobic buffered reactor refers to a tank or system that has several compartments or sections, and in between it has these kind of walls that create these compartments, and then the fecal sludge or the toilet waste goes into the first compartment and then overflows into the second compartment and so on. So an ABR may have, as shown in this one, 5 or 6 compartments until it goes to the next step. So in this process, this is especially relevant for fecal sludge. As mentioned, fecal sludge is potentially rich in pathogens, especially fresh fecal sludge. And these pathogens don't just disappear after a first treatment step. So if you just have the biogas settler, your fecal sludge goes in there, and then you would use your digested directly for agriculture purposes afterwards, you may risk that you have pathogens that you spread on your field, on your vegetables or fruits, and thereby also creating a health risk as well as environmental risk. So instead, for fecal sludge, you always require several treatment steps. And that, as proposed here, would be to let an anaerobic baffled reactor follow your biogas settler. Last but not least, we have here as the another example, the anaerobic lagoon. What in this dimensions is more of a centralized system and the equivalent to the small balloon digester that was shown before. So here you have the same principle. It's like a combination of a whole partially underground system where the fecal sludge flows in, and then with every new substrate being flown in, it's slowly being pushed throughout the rectangular system towards the outlet, and the biogas at the same moment is stored in the upper part, and you see as when you don't have a double membrane but a single membrane, you will see how much biogas is being produced. So here partially on the picture you can see some higher parts of the membrane indicating that this is especially where the biogas can be found. So it's not being filled at this stage. Here again, a little question for in between. What is the primary purpose of a biogas settler or biogas septic tank? Okay, this was quite the mixed reply. So let me explain this a bit more in detail. So all of the above would have been the correct reply. So I think everybody is clear on the fact that the biogas septic tank or biogas settler is intended to facilitate the anaerobic degradation of solids. So that is clear, as it already says with the settler septic tank. Then we have to promote the separation of solids and liquids. This is very common in the septic tank as a first step. So septic tanks, you have the fecal sludge coming in, and then you have usually the solids remain in the system, and the liquid, lighter effluent part goes out through a different outlet, while the sludge remains in the tank and therefore requires desludging on a regular basis. So that's why a septic tank is considered as also used as a first step to promote separation of solids and liquids. And if it is an airtight system, in that case, if it would only be a septic tank, you would release the emissions or biogas directly into air. But a biogas septic tank foresees that you close the system and collect the biogas, capture the biogas, and make use of it. And by closing up the system, making it airtight, you facilitate an anaerobic, oxygen, air-free environment ideal for the degradation of solids. So last but not least, we come to the final section of the presentation. How can the implementation of a biogas system in an emergency setting look like? And for that, I want to go with you to a specific example, what can be found in the Rohingya refugee camp in Cox's Bazar, Bangladesh. What, as we know, is one of the biggest, unfortunately, one of the biggest refugee camps we found. And here in this picture, you can see a toilet block, as well as a biogas digester, or the upper part, the above ground part of the biogas digester here. And this system, well, it is not covering the entire camp population. I mean, the camp population is almost 1 million individuals. So you have, if you would really cover the entire camp population with different biogas toilets or biogas or toilet blocks connected with biogas digesters, as shown in this picture, you would be able to produce 10,000 to over 20,000 cubic meters of biogas per day. So this would also translate into very substantial LPG potential. This is just a rough estimation, as these biogas digesters connected to toilet blocks is just one of the technologies that is applied in the camp setting in several cases. But nonetheless, these systems, as well as they are in the way of like what potential they bring and also how they benefit to create a more safely managed sanitation environment, and also at the same time provide families with biogas for cooking. There are also several identified challenges that I want to talk about, as well as some solutions. So especially for you that are more interested in the practical part, I think this part of the presentation will be very interesting. So one of the main challenges identified and can be seen also in the picture is clogging. So this was in more than 60% of the biogas plants experienced was clogging of pipes. And this is occurring often, as you see, the piping diameter may be not huge or large in that sense, based on also your availability of pipes also, or your design. And if you then dispose a lot of other debris in the toilet system as sanitary pads or this wet toilet papers that are not that easily disposing, then they can build up and cause the clogging of the pipes. So what is essential in this regard is that you need the piping, like in the worst case, you need to redesign your piping system overall, provide also larger piping diameters or regular maintenance and cleaning schedules. But the most simply part is to well, not the most simple, but you would hope that this is what the direction goes. It's a higher awareness that people don't dispose waste that is not supposed to go into a toilet, that they dispose it into bins next to that should be provided in the toilet blocks, or also built-in screens that separate all the inorganic waste and only lets the organic waste pass into your system. Another challenge identified was the condensed water in pipes. This is like your biogas pipes. When your biogas exits your digester and goes, for example, to the cooking stoves, there may be a accumulation of water, depending also on how you have installed your pipes. And this may lead to corrosion, reduced gas flow, and at the end, increased maintenance requirements. In the worst case, your gas may not even arrive at your stove, and you may think that your biogas system is not working properly. And the condensed water is always building up in the lower sections of your pipe, as it's shown here. So here would be, for example, water built up as this pipe is hanging lower in this section than as in the other. And the most simple solution that you can if you build in a trap, so that the biogas can the water can exit here. Last but not least, you have the gas leakages. This again, depending on how, if you have a lot of connections here and there may be a risk of gas leakage. And this also is then a risk for safety and also a loss of biogas and the cost for emissions again. So you would need to check your fittings and unions, and ideally do at the end of your installation and also on a regular basis, just gas leakage tests as it's done here with soap. If you put soap water on a potential area where you think leakage could occur, if there are a lot of bubbles, then it indicates that there's a gas leakage and you need to improve this section. And last but not least, we have the effluent management. Now, there is a frequent desludging of the collection chamber still necessary unless you have the post-treatment for your fecal sludge after the biogas settler already set up. You will, similar to a septic tank, arrange the collection or the desludging. Although compared to septic tanks, the desludging rate is decreased. So before, with a septic tank, you may need to desludge 6 to 12 times a year. But with a biogas system, you reduce the digested quantity as part of the organic matter is transferred into biogas. And it may only be desludging twice a year. And if you don't dispose of it properly, then you also have, again, what I mentioned before and what we discussed, the risk of pathogens if you use it directly. So then again, you either need to have a very well centralized system or a very well functioning post-treatment system that you have to set up. So I hope this was quite interesting for you. I have a last question for you here again that I would ask you to participate in. Okay, so maybe just 4 people. Then let's do this final question. What is a major reason for the clogging of black water inlet pipes and biogas plants? Nice. Okay, then we can all agree on the answers. This was very clear. And with that, I very much appreciate all of your participation in this kind of test, and I would like to look with you at the leaderboard. I mean, it is anonymous, so we don't see who is who, But congratulations to ET for winning this quiz game based on your correct answers and fastness in answering. Congratulations. So with this, I thank you very much for your attention. And I hope I made you think about your biogas potential of your poop, because from poop to power with biogas, turning waste into valuable energy instead of just flushing it away. Thank you very much. And if you have questions, I would very much like to give you the answers. Thank you. Are there any questions, comments, or remarks? Martin, please.
Yes, thank you very much. Coming back to my question about the NC ratio or CN ratio, is there a simple way of measuring this ratio, or is it just by looking how the digester works?
No, you have values for different substrates usually already available online. There are databases that provide this information, and then you would just need to do a simple calculation. And based on that beforehand, you can already make assumptions. Of course, in the practical life, I mean, what you do, you could also test it on laboratory scale by combining substrates or testing the substrate on the carbon and nitrogen contents. Then, of course, there's a risk that in real life it may be different. Like if you have a big system, and then you have to find a solution in that. But usually there are already quite a lot of tests that, or first you can do the calculation, then you can do the test on laboratory scale, and only in the final solution, if you still have trouble with this ratio during your operation, you would need to find a solution. Does it answer your question? Okay. Thank you. And the exact calculation and how you do this, you can find also in the online training. Any other question? Zubin?
Thanks a lot for the informative presentation. I just wanted to know about if there was any ways or anything, any kind of, what can you do to increase like community acceptance of biogas in communities?
You mean if there are initiatives to do this, or
yeah, so if there's any methods, or how would you go around increasing community acceptance for biogas and sanitation?
Yeah, so of course awareness raising is always important, and also integrating the feedback or the people itself. I mean, should not just set up the biogas system without involving all the stakeholders and the community, especially also in the camps itself. So even beforehand, before implementing the system, discussing the idea, there is already communication with the camp population to see their feedback, and also to show them the advantages of biogas, how it works, since they are also more the ones, unless, I mean, you may assign an operator, but still the daily interaction, as for example, as I mentioned, it's important to not throw any inorganic waste into the toilet or so. So if you do a lot of awareness raising along the way, that is also usually done, then yeah, these kind of system problems may also be more avoided at the end. For specific activities, I also referred to the online training as we have that explained that a bit more. Thank you very much for your participation. So, and I would very much encourage you again to check out the online training. And if there's any feedback that you can provide, you can also send it to this email address, or if you have questions that came up throughout the training.